In this video, we'll look at the large deflection switch in ANSYS Workbench 14.5. In linear analysis, one of the major assumptions is small displacements. The resultant deformation is only then in the direction of the load. In this case, if we have a beam that is constrained at point A and we apply a vertical load at point B, we will have a resultant x direction displacement of 0 and a negative y displacement. In reality, however, we'd expect deformation to follow a curve path. In this case, dx would be negative, and the y displacement would also be negative, following this curve path. Let's take a look at a representative ANSYS model. Here we have a beam model that is constrained on the left-hand side, and a sizable load in the y direction is applied on the right-hand side. Note that the end of the beam becomes greatly exaggerated in this linear analysis. On the plot of x direction deflection, the magnitudes of the max and minimum are about the same, around a 0 center. If we stop the animation and probe the center line of the beam on the end face, we see that the resultant deflection in the x direction is 0. In the next set of results, I've turned on the large deflection switch in the analysis settings. You can see now in the true scale results that the beam keeps a seemingly normal shape, and the response to the load is along a curved path. This is more along the lines of what we might expect as the beam continues to bend from the supplied load. As a confirmation, the resultant x displacement is much less than 0. In another example, we have a sheet body with a uniform pressure applied, with fixed constraints around all edges in a linear analysis. If we look at equivalent stress, it shows that most of the model is exceeding yield for an average structural steel material. The exaggerated deformation plot shows that we are seeing about 176 millimeters of maximum deflection. With the large deflection switch activated, we see now that the stresses have come down drastically. Furthermore, the deformation is over an order of magnitude smaller. In conclusion, the linear geometry approximation is commonly used successfully in structural analysis because of the relatively small displacements associated with many structures under loading, especially when operating inside the elastic limits of the material. Certain structures benefit more from the large deflection switch. Pressure or load applied to a large unsupported sheet metal surface is one such example. As a general statement, the large deflection switch in the analysis settings provides a better representation of displacement and results otherwise, since most other results quantities have their origins in displacements. Note that because of the introduction of nonlinear behavior to your model, the runtime penalty can be significant, and engineering judgment should be exercised on its usage. Thank you for watching, and have a great day.